Hello and welcome. Welcome to our mini symposium in honor of JILA's 60th anniversary. Today we've got 3 talks. They are covering both historical strengths of the Institute as well as some new research directions. Please do not be disturbed that I've put a tie on. You should really regard this as predominantly a scientific symposium. Please ask questions, treat it like you would any other scientific meeting. There will be, I guess, 2 important differences. First, I will be really strict about keeping us on time. So immediately following these presentations, we'll all go over to the case building for our celebration of major prizes. And there we'll have some high-profile university and NIST officers and other dignitaries. They get to be late, we have to be on time. Second, we're holding this event at the end of a long period of having been remote from each other and our colleagues, and we're going to take the opportunity to mark some occasions which we didn't have the opportunity to do in person. On that note, that really brings me to the first speaker in our symposium, Professor Carl Lineberger. Carl received both his Bachelor of Science and PhD degrees in, and I did not know this until I read your bio, Carl, electrical engineering at Georgia Tech in 1965, working with John Hooper and Earl McDaniel in atomic collision physics. In 1968, he began postdoctoral work with Lou Branscombe here in JILA, and subsequently joined the faculty at the Department of Chemistry and Biochemistry at the University of Colorado. He's now the EU Condon Distinguished Professor of Chemistry and Biochemistry and a Fellow of JILA. And Carl is a pioneer of using laser technology to study chemical processors. For his field-defining work, he's been awarded the H.P. Broida Prize in AMO Science, the Earl K. Plyer Prize by the American Physical Society, the Meggers Prize by the Optical Society of America, the Michelson Prize by the Koblenz Society, the Irving Langmuir Prize in Chemical Physics, and the Peter Debye Prize from the physical chemist in physical chemistry from the American Chemical Society. He is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, Fellow of the American Physical Society, and the American Association of the Advancement of Science. He's a member of Sigma Xi and the American Chemical Society. In 2015, he won the National Academy of Sciences Award in Chemical Sciences. In recent years, Carl has been involved in a number of science advisory activities. He served on the Council of the National Academy of Sciences, the governing board of the National Research Council. He was a member of the National Research Council Committee on Science, Engineering, and Public Policy, and he was the chair of the National Science Foundation Advisory Committee for Mathematical and Physical Sciences. Currently, he serves as consultant to the National Science Board. Okay, Carl's talk today is going to tell us, I think, some fun JILA history, and then we'll take a few minutes to acknowledge and recognize what is a kind of bittersweet occasion, the retirement this year from the University of Colorado. Welcome, Carl.
Can you hear me?
Yes.
Good sign. I decided that by far I preferred to stand facing you rather than having my back to you. So this is a much more comfortable thing. If I see someone sleeping, I have a laser. No, seriously, it's really an honor to be here and talk to you for a short period of time. I hope you'll notice this is supposed to be, Konrad, less than an hour, as I recall. There you go. By a factor that we won't discuss, but I think it's 4. Anyhow, since coming to JILA, JILA is a place that really provided an opportunity for diversity and to work with some very smart people. And I must say, I cannot imagine a better place to have spent the last 54 years. And this will always be very deeply in their memory. Okay, let's see what happens, SV, if I say magic. There I am. Oh, okay. That looked like the thing I just saw. Let's go again.
We did test this, I swear. Try one more time, Steve.
Success. Success. Today, I'm going to use my time to take a rather small number of topics and talk to you about what is it that makes JILA special. And I think there's a lesson that all of us need to learn. And the key to it is dedication and having great people around you and listening. And as you'll see, that's what we're going to be doing. So you could say, oh, that got there very quickly. Jan Hall, who is watching remotely, I'm told. Jan, hi. I hope you don't mind my telling a bit about the Poor Man Mine, because that is a key piece of early JILA history and an unqualified success at mapping multiple disciplines together, and is really a model for doing this right. So let's go. SV. There we are. Okay, I can see the Poor Man Mine here, so I don't have to do that anymore. Jan was and is a superb precision measurement laserologist. But when he first was here, they were developing precision laser measurement methods, or stable lasers. And there was a JILA postdoc named Dick Zare, and who knew some chemistry, unlike most of the rest of us. And Jan talked with Dick about what should I use for a saturable absorber. I'm not going to tell you what I mean by that. That goes in the laser cavity and can enable you to get much better line widths with the right material. And Dick paused and said, methane. He was right. I mean, they were running around 3 microns. That's the basic fundamental absorption area for methane. And it made a huge impact in precision laser measurements at that time, by sort of orders of magnitude. So if we look, one of the things that you can do with stable lasers is you can make a cavity that is ridiculously long. Jan had a cavity in the sub-basement initially, of a big pipe running across the ceiling, which got moved into the sea wing and continues to be used. But they were interested in looking at things, the tides of the Earth, as the moon went around and deformed the Earth. And so what they did is they set up a high resolution laser system in the poor man's abandoned gold mine. This mine is up Sunshine Canyon, half dozen miles or so from here. Really not a bad place to be. But let's keep going. Okay, here it is. These pictures aren't quite right at this stage. But this is looking into this 30-meter long interferometer with the 2 mirrors at each end of the laser being tied to bedrock in the cave. And so the idea was that if things came along and moved those, made differential motion between these 2 pieces of bedrock 30 meters apart, that you would see it in reflected in the change in frequency of or intensity of the laser as it came out of tuning. So this worked remarkably well. And it was an absolute tour de force, other than the fact that you had to build a precision laser system in an abandoned gold mine way underground with your mirrors on bedrock. But obviously it could be done. Judah Levine, where are you in here? There you go. Judah was another of the very early participants in experiments in the poor man mine, and ask him hard questions at any point. So passing on, this is that's how you get on. But they were measuring the earth tides, and this was a very sensitive measurement in the sense that the kind of displacement they could see between these two changes in displacement. They could see to it down to the size of roughly 1,000th of the diameter of a human hair. In a 30-meter system, that looks pretty damn good. So there was a lot of use of things like earth tides, but then something changed as a bit of a surprise. Next slide. There we go. Where things were going along smoothly, and all of a sudden, all hell broke loose. We're looking like normal tides, and then all of this high amplitude motion. And guess what it was? It was an underground nuclear test at the Nevada test site, 1,000 miles away. And they realized they had something, and took considerable advantage of it, I would say. But among the things that sort of happened with that is the stability let us see things. I'm trying to get caught up with starting too slowly. After it became clear that that's what Jan had seen, they contacted the Defense Department and said, you might be interested in knowing that you set off a nuclear detonation at the Nevada test site at the following time. This was in the late 60s. We were as close to being at the peak of the Cold War as you ever get. And there was a lot of trigger happiness at that point. That was sufficiently impressive that they noticed, I mean, the defense people seemed to take this a bit to heart. And so a month or so later, they were doing the same test again. And this time when there was a detonation, the rise time was much slower. And Jan wrote back to the DOD people and said, I think you put metal shards in the cavity. And yes, that's what happened. Just to sort of bring this to a fairly quick halt, the thing I wanted to really emphasize is that Jan talked at a 1968 conference in Warsaw about this kind of process. And what can you say? The ability to make these measurements did not really go overly well with the Defense Department. But the thing that did come out of this that was, I think, very important is that the ability of this interferometer to be so sensitive about detection gave you a way of seeing what the other side was doing. And this played a huge role at the time, particularly after this meeting, of generating US support for the 1968 nuclear non-proliferation proliferation treaty. It's not the kind of physics you think about every day, but it's science that makes a difference. And you really can't ask for much more than that. If I continue on now, I'm going to leave that aside. Everybody recognize who these are? Their names are given somewhere. There's Judah and Margaret Massey, who were continuing much of the laser interferometry, and we're doing a lot of other neat things that I clearly don't have time to say much about. I wanted to pick this as an example because this isn't what we traditionally do, but an institute like this can still make a huge difference with the set of technical skills that can be, I'd say, called upon to make key contributions, with the whole being a hell of a lot more than the sum of the parts. And I probably got about 2 minutes left. Is that your guess? You said 20? I don't believe it. Anyhow, what makes all this happen? Ed Condon came to JILA very early on. And I want to tell you the story from a personal point of view, because in my view, this is actually a tale of one of the best things the University of Colorado managed to do in the last 40 or so years. Ed's leanings were certainly politically to the left, but he was not communist. His wife was a little more than active, but Ed started as director of the National Bureau of Standards, now NIST, and the congressional harassment that came from the McCarthy issues forced him out of that position. He was able to get a position as chief scientist at Cornell Glass, and in a short time, he was forced out of that position. Essentially, they were taking this guy who was an absolute one of the pioneers of quantum theory, and like front Condon factors or a few other things, and were making him unemployed. Lou Branscombe of course, had been at NIST and was able, so he talked to Ed and found out Ed would come if they made him an offer. The university, to my shock at this stage, managed to offer him a non-tenure track appointment, which served at their pleasure, such that he could be fired at any moment. Well, he did a lot of good for the university at that time and was easily the best recognized scientist here at the time. I'll leave it at that. Let's just say it made me proud of the university. I'm not sure they thought it was the same. I'll give you one quick story and then shut up on that. But when Ed was director of the old National Bureau of Standards, he was testifying in Congress for their next appropriation, and the chair of this appropriations committee turned to Ed and said, "You know, I visited NBS yesterday, and I walked through the building, and I found 11 typewriters that were not in use." And you think, come on, what are you doing? Well, Ed's answer was, that's very interesting, because sometimes when you need them, you need them. But when I was walking through the Senate Hall to get to this hearing, I passed a number of restrooms along the way, and none of the urinals were occupied. What do you think about that? You got to say he's quick. Anyhow, what makes JILA what it is? With two quick slides, keep going, there you go. The most important thing that we have to make us work is a high quality staff that are here to do so many things. And some of these you'll recognize, some of them even sit in the front row wearing a mask, but that's
Weird.
One of these people whose name shall remain not mentioned managed to get me a parking pass for right behind JILA for today. So yeah, obviously good taste is being shown at every level. So, and of course, what makes the place work are the students, the postdocs, and for that matter, the fellows aren't all bad. And let's go to the next. Okay, here are the visiting fellows, somewhat out of my. This is a picture you've seen somewhere else in the building. I just want to show it because it's such a interesting representation of science as viewed by a Czech scientist and artist. And there are details of this I won't mention, but that's okay. So let's go to the next slide to get further to the end. JILA started out in 1964 with 12 people coming from Washington. This is JILA today. That's pretty significant growth. And thank goodness they did. And it was an exceptionally wise thing. That's really about all I can say. So let's go to the next slide. I just wanted to remind us that we're a pretty cool place. And you will hear later in the day from Eric Cornell about their Bose condensation work. Jan, who's listening, but not here in person speaking, received the Nobel Prize for the kind of work that I've been talking about today. And so we have 3 Nobel Prizes coming out of the work that I've mentioned. And I would almost guarantee that there are going to be more. And that's part of it. So much more lies ahead for JILA. And I wanted to end with a commercial because Margaret and Henry have both won major awards. And they, Margaret Henry and June won the Breakthrough Prize in Fundamental Physics in 2022, and Henry and Margaret, if I get it straight, received the Benjamin Franklin Award for Physics in 2021. These are outstanding recognitions, and again, things that can make us proud. After this is over, you can go over to the case. And there you'll be free admission, and you get to hear our chancellor speak his usual wisdom. And I'll let you think about that. No, thank you. And let me tell you, it's been a wonderful run of 54 years.
So, and where's my
The clicker.
advance?
The clicker.
Good. All right. Well, this is such a pleasure. I mean, this is continuing a bit in the same vein, but of a more personal connection in some sense. Carl and I, we've known each other since I was a high school teacher, and Carl invited me to actually come up to Boulder and develop labs for the PChem course. And that's more or less the reason why I'm here today, some 50 years later. So, so let me continue in this sort of tradition. This is now the 60th happy birthday celebration for JILA. And really, this has just been 60 years of fantastic physics, but very much as Carl has indicated, it's this combination of multiple skills, brilliant, hardworking grad students and postdocs super talented staff, instrument shops, computing, electronics, supply, just everyone is really high morale and high talent and excellence. So I say, yes, JILA takes a village, but most importantly, that village has got to be filled with the right visionary and selfless citizens. And I would say that Karl Lineberger is an absolute fantastic example of that. So this is really just sort of a bit of a, thank you, Karl, right? And I'm going to thank also Kitty Edwards and Steve O'Neill in advance for giving me just fantastic photos. This is mostly just a photo journal, if you will. Okay, so let me tell you a story about Karl. This is something gives you a sense of what the early Karl was like. Of course, came to JILA as a postdoc for Lou Branscombe. One Thursday in 1969, he challenged the electronics shop to build a nitrogen pumped dye laser. Okay, he worked through the weekend, which, if anyone knows Karl, is absolutely no surprise. He took the first tunable photodetachment spectrum of S- Monday, and then submitted a paper to Phys Rev Letters that following Friday. Okay, so that's sort of Karl, right? So he joined chemistry and became a JILA fellow in 1970. And here's this remarkably diverse photo of the JILA fellows back 1970s. I'll give you a little bit of time to find Karl, but there he is. And I have some of the names. I don't really have all the names, but maybe you guys can help me later on, but of some of the other fellows at that time. Okay. Now, Karl, he's a stylish guy. He's really right? Handsome, right? And Karl, you used to wear these shirts all the time, right? And never washed, right? Well, you'll see that he got other people in a bit to wear them as well. But the story is that science funding in the early 70s was really dominated by the Vietnam War. It was dragged down. And Karl and David Hummer, here's David, just did something very special, really game-changing. They went to NSF in 1973 and they lobbied that what they should do is get a group grant that would fund something like a dozen JILA scientists. That grant, in one form or another, has lasted for the past 50 years. It's currently the Physics Frontier Center. And Karl served as the PI for that grant for 40 years, 4 decades, right? So think about this: stable, long-term funding. I put stable in quotes because we never really feel it's stable, right? But with built-in encouragement for interdisciplinary collaborations. That just completely was absolutely at the center of gravity of JILA. And that was a complete game changer for the science at JILA. And I think it's fair to say, Karl, that really changed NSF in the way they approached funding science as well. So good. So, all right. So keep in mind that spiffy shirt, right? Okay. So new faces join the JILA Karl Lineberger team. We have David Norcross there. We have William P. Reinhardt here. We have, Steve Leone. Steve, you must be on Zoom. I imagine you are. Yes, sure you are. Okay. And this is sort of a picture of sort of the Karl Lineberger group, sort of the Ion group at the time. We've got Steve, we've got Chuck Depew, Eldon Ferguson, Ronnie Bierbaum, Barney Ellison, Karl, of course, and Zdenek Herman, right? So anyway, just sort of a wonderful sort of a group, a team. But there are, of course, many postdocs and students and staff joining the team as well. So I have like little vignettes. There's Steve O'Neill as a young kid, Barney Ellison. Here, there's me playing shortstop. Here, Krista Beck, right? Ronnie Bierbaum, I mean, just lots. In fact, in this very fuzzy photo, we have even Dan Newmark. And then I think in the back, isn't that you, Mark? Yes, right? So we have representation on, and Jan always used to talk about what's the secret sauce of JILA. I'll tell you what the secret sauce is. It was round the corner. You may not know, but basically all of the people that came to JILA on Saturdays, we'd all go out and we'd have hamburgers together at Round the Corner. Yes? Does people remember that? Yeah, Bill remembers that for sure. Okay, so we'd talk, and Jan would talk about Poor Man's Mind and whatever, and you know, the chemists would listen to the physicists and vice versa. It's fantastic. So here's, I think, a really sweet picture of Kitty. So this is New Love Joins Two. Look at what a charming pair. I mean, just amazing. So Carl and Kitty got married in 1979, and that basically sort of, you know, his scientific productivity doubled, right, in 1980, right? Okay. So I want to give you just some faces of Carl, right? Several faces. Carl is CU educator, right? So first of all, he's youngest distinguished professor at CU, you know, youngest when it was awarded. He really had, in ways that you might not see, but you know, he was an innovator in involving undergraduates in courses in the chemistry department. And I think they even are on papers that were submitted to the literature. So fantastic stuff. This is something that only the old folks like me remember. Mark, do you remember the Wednesday evening seminar series? O'Neill does. Yes, Bill does for sure, right? The Rheinbergeroni. This was back when you could actually give beer to graduate students. That's how long ago this was, right? This was called the Rheinbergeroni, or the Rheinbergeroni. And honestly, that became as well known as the JILA Visiting Fellows Program. You talk to people around the world and they go like, are you still doing those Wednesday evening seminars? They were fantastic. Carl as mentor. So this is just, again, sort of a little bit of a photo collage of the different people that have been in Carl's group over the years. And I include, I guess at the very end at least, well, let's say, hang on, it's coming up. Yeah, there's, you know, good old Mark Johnson. There's Dan Newmark. Hey, there's a young David Nesbitt. That's Tim Zwier. You know, we were mentored. I mean, like, be a graduate student, be a postdoc, be a fellow faculty member, whatever. Carl, he's just a supreme mentor of all of us. It's just been a delight. Here's actually, this is really his group, right? This was 40 years of ion chemistry. I think, Carl, you officially had like 83 graduate students over your career. This is a little more than 83, but basically it's the entire collection of people that Carl worked with and mentored. Carl is amazingly talented. He is an architect, right? So when Carl was chair, 1985 and 86, he raised funds from NIST and the Department of Education. How many people have grants from the Department of Education? Not me. And he oversaw the financing, creative financing, design and construction of the new S-Wing building with David Norcross. So this is really what the S-Wing looked like before we had the new X-Wing. And you can really thank Carl Lineberger and David Norcross for this, okay? Carl is scientific statesman. Konrad has certainly talked about this. Years and years of service on national, international committees, National Academy of Sciences, National Science Foundation, 2 terms on the National Science Board. But what I'd like to say is that his all-time favorite institution was always JILA. And so here are some pictures. Carl at the South Pole and Carl at the, you know, at DC with the head of the National Science Board and the head of the National Science Foundation. Here's another trick that Professor Lineberger always had. He is the original quantum mechanical object. He's the delocalized quantum state. Now, we saw Zdeněk Herman. Carl was talking about him. What a cutie. I mean, like, you know, that's pretty amazingly good looking, right? So this is Zdeněk Herman and then the cute Carl Lineberger. And here's Zdeněk speaking, I believe, with Ugo Fano, right? Yeah. But hey, do you notice the shirt? Okay, right? He got Zdeněk to actually wear these cowboy shirts, right? Fantastic. So this is this famous sketch that Carl talks about. I think I looked for it in the 10th floor, but I don't think it's on the 10th floor anymore. But Second floor. Okay, please go look at it. And what you'll notice, the amazing thing, this is of course by Zdenek Herman, is that Carl appears in 4 different places in this sketch, right? And so, really, this is an example of Carl completely, ahead of the pack. Carl Quantum 2.0, right? Carl was really the original entangled quantum state and appears 4 times throughout this. It's quite fun to look at. So anyway, I just really want to say my personal gratitude for all that you've done for JILA. Thank you.
We have an Eric.
Very good. Our next speaker is Professor Eric Cornell. Of course, within JILA, we know these facts well, but if you're visiting Bachelor of Science in 1985 from Stanford, 1990 PhD from MIT, and then in 1990 to 1992, he was a postdoc here in JILA, and that's where he currently is as a JILA and NIST fellow and adjunct professor of physics. Eric's work has been recognized in many awards. I won't read these ones. The one that will sort of trump them all is the 2001 Nobel Prize in Physics for the achievement of Bose-Einstein condensation in dilute gases of alkali atoms, et cetera. And so I think with that, I actually don't know that I have a title for your talk, Eric, other than Spotlight on Awesome JILA Research. Go ahead, Eric.
Thank you. Thanks very much. I have a chip for a clicker. Should it go in here if I want to click my own slides? Is that? Oh, it looks pretty much the same, yeah. Except this, they're exactly the same, except this is my lucky one. All right. Well, if I have bad luck, you'll know why. It's because I'm not using my lucky clicker. The only thing, I could add many things to what David said. The one thing I will think about, just want to mention in particular, Carl, is that you had a realization very early on that JILA can never just be about one person. JILA has to be something about an ongoing, a continuity. And you always had this idea of bringing up through JILA people to be good scientists, but also people to sort of look after JILA a little bit. And I think we have around JILA now, we have a cadre of fellows who are interested in the future of JILA. And it's because you did not sort of say, I am the director of JILA, but rather said, well, I'll bring this. So at a very baby-faced young age, for instance, I was sitting on various executive committees, and many of my colleagues of roughly my age or younger had this experience too. And I think it's a tribute to your vision that it's like, yes, you've been enormously important to JILA, and not least because you realize in the future other people will be important to JILA and they need to be brought along. I just really admired that foresight. So maybe I'll turn this on. So thank you for both 50+ years of leadership for JILA, and for me, roughly half of JILA's age. I've been here. It's a personal mentorship, which I so appreciate. I want to talk about looking for fossils of the Big Bang in the laboratory. So that's the title, which I forgot to pass along to. What do I mean by fossils? First, let's talk about the Big Bang. This happened, the Big Bang happened 13.7 billion years before our 60th anniversary. For those of you who are quick with your algebra, you realize this happened quite a few years even before the beginning of JILA, as old as JILA is. There was a Big Bang. A lot of this is inferred. Not many of us can, even Carl may not remember this exactly as a personal memory, but there was a Big Bang. Afterwards, as the television-based creation hymn goes, the whole universe was in a hot, dense state. It was full of electrons, protons, neutrons, anti-electrons, anti-protons, anti-neutrons, just about almost exactly 50-50 of each of them. And then the universe expanded and has expanded. And we learned in chemistry class, I actually have taken one, as gases expand, they get colder. And that's what happened to the universe. It expanded and it got colder and expanded a little bit more. And then something very romantic happened. Each particle found its true soulmate. The proton found its antiproton and so on. And it was really quite adorable. But these marriages were passionate, but really quite short. They hooked up, they annihilated, and they were disappeared, leaving nothing but photons behind. It's really a story of all-consuming passion. And all around the universe, this is what was happening. In the mass cosmic wedding that happened just a few hours after the Big Bang, there was somebody for everybody, except, wait a minute, what about those electron, that proton and neutron? Almost there was something for everyone. If you looked around the universe, there were a very small number of matter particles, what we now think of as electrons and protons and neutrons, that weren't able to find a date on this colossal New Year's Eve. And so who are these sort of lonely particles that no one wanted? They're you, basically. Those tiny few lonely particles joined together, and we're happy they're there because they formed hydrogen and galaxies and what have you, and eventually JILA and us. So, but still, it's when you think about, the existential angst of life, I feel like this particular fact explains a lot. All right. What was nearly perfect, the fact that it turned out that for every billion protons, there was antiprotons, there was a billion plus one. I got that backwards. A billion plus one protons for every billion antiprotons. But so it wasn't quite a billion to a billion. It was off by about a part in 10 to the 9. And because of that tiny little imperfection, this deviation from perfect symmetry, the whole universe came into existence, and we were born of this original imperfection. And that's what it looks like, I'm told. We recently took pictures like that. And all of those galaxies are also, just like us, made up of matter and not antimatter. And you can tell that because in those places where one galaxy overlaps with another galaxy, if one of them was matter and one of them was antimatter, you'd see a lot of intense gamma rays coming from the sort of corners between the proton, where the galaxies touch each other. If that doesn't happen, we know that all of those galaxies are all matter, just like us. And eventually those galaxies evolved, and one of them generated JILA. All right, so the question I want to ask, or many people are wondering, is like, how did this come to pass? And how can we learn more about this fundamentally important asymmetry? We can't read about it in the history books. There's no history books. There are no written records on papyrus rolls. How can we look at it long ago? And I'll argue that there's sort of three basic ideas of how you can look back in time that far. And one leg is telescopes and telescope-like things. And I include LIGO in this, but basically anything that can look, this is going to be, not yet, this is a conception for a very, very large telescope that looks far back into the future. Gravity waves are also basically a telescope. Underground observatories, basically I think of them as one of sort of the inheritors of the poor man, or these things in South Dakota and what have you. Deep underground laboratories. These all basically look at things coming to us from far away. When you look at something, when you see a galaxy or anything which is 10 million light years away, you're actually not seeing it the way it is now. You're seeing it as it was 10 million years ago, because that's how long it took the light to get to us. The furthest galaxy has anyone ever seen, and this slide is old, so this is probably out of date, is 13.3 billion years ago. This picture we have of this galaxy, we're looking at something which was a galaxy that existed when the universe was only 4% as old as it is today. And yet that is not far enough away, or to put it another way, not deep enough back into time, because by the time these galaxies appeared, this fundamental asymmetry had long since happened. The protons had overwhelmed just barely the antiprotons. So that's one thing. Another thing is, well, let's just simulate the Big Bang. We'll take a proton and an antiproton will smash them into each other, and there'll be this very small but intensely hot thing, which will be something like the Big Bang. So towards this end, and partly motivated by this exact story, they built the Large Hadron Collider, the largest scientific instrument ever built. And here in the world of small physics, we can all just say it was a little bit of a disappointment. They did not see the answers to these questions they hoped to. So it was apparently not able to answer this question. The next generation Large Collider may be 3 times 10 to the 1 years away and 3 times 10 to the $11 away. You know, it may not actually ever happen. And in the case, it won't happen for 1.5 scientific generations, maybe 2. The idea number 3, and that's what I'm going to talk about, is we look for fossils. That's how we see dinosaurs. There aren't any actually written records by dinosaurs, but you can find their bones. Are there fossils today of the Big Bang? That's what I want to talk about. It has to do with symmetries. This is a beautiful case of symmetry. I just put it up because it's such a beautiful picture, but I'm actually talking about more microscopic symmetries. There's 3 major ones in the world of physics. One is that electrons act just like anti-electrons, or protons like antiprotons. Matter and antimatter are about the same. The other is that particles look very much the same. Electrons and other particles look the same in the mirror. It's true for particles. It's less true for macroscopic objects. Here's someone who we can't tell. Well, you could tell right away if this person is missing a left arm or a right arm, whether they're looking in the mirror or not. It may not be a coincidence that my experiment to study these asymmetries of the proton started in 2004, the very year I became a profoundly asymmetric person. Who knows? You know, one of these days I'll go into psychoanalysis and we'll probe this, but there it is. Also, the final one is that on a microscopic level, particles look the same if you run the movie backwards. And that's not true. If I drop an egg, you can always tell, like, yeah, that movie is running forward because the egg is smashing. But on the most microscopic level, if an electron bounces off of a proton, if you take a movie of that and you run it backwards, you can't look at the movie and tell which way time is going at the microscopic level. Okay, these 3 things are all pretty good symmetries, maybe not perfect symmetries. But the fact that there are, did I push the mute button? No, I just broke it somehow. What did I do? There's this, whatever it is, I fixed itself. That's good. I'm not going to get into this exactly, but because it's getting beyond the scope of this talk, but these various asymmetries don't come individually. They come in groups. Basically, if one of these tenets is violated, other tenets have to be violated as well. And in particular, if there's something that makes electrons a little more plentiful than anti-electrons, other things like this time reversal thing have to exist as well. And the key assumption, and you could call it a faith if you like, is that the rules of physics back in the Big Bang are the same as the rules of physics now. So there should be leftover asymmetries, fossils of the Big Bang. And when we look around them and study particles today, we do not see them. We don't see an asymmetry in the existing particles big enough to account for this. What's called the standard model of physics, which is everyone's favorite accounting of how particles work, doesn't contain in it enough asymmetry to account for the fact that we're here at all. So we're going to go look for it. And in particular, we're going to look for it in a very humble particle, the electron. There are a lot of theorists, and I'm not one, and they're explicitly particle physicists, and I'm not one. They all really feel like these fundamental particles ought to have electric dipole moments based on the same physics that gives us this asymmetry that allowed the universe to exist. That's all I'm going to say about the theory behind it, because in the end, I'm kind of an oscilloscope laser sort of person and less of a Lagrangian particle physics kind of guy. All right. Here's Mr. Electron. I don't know why I gendered electron. It doesn't necessarily have one, but it definitely spins. It's got a negative charge. It spins. It gives it a magnetic moment, a north pole and a south pole. And it's got a spin, and that gives rise to it because it's charged. It has a north pole and a south pole. The question is, are the north pole and the south pole exactly the same? They don't have to be. Here on Earth, we have a north pole and a south pole, and they're quite different. The North Pole is sea ice, or when I made this slide, the North Pole was sea ice. You can tell that tells you how old this slide is. Now it's sea, I should say. South Pole is mountains. In one place you have polar bears, the other place you have penguins. If you see polar bears and penguins in each other's company, you're in a zoo. right? Doesn't happen anywhere else. So what do we know about the electron? What could be asymmetric? Well, it's mostly negative, but it could have a little more positive charge near the North Pole, a little more negative near the South Pole. And if it did, it would have so-called electric dipole moment. And that's what we're looking for. If it exists at all, we can describe it as the center of mass of the particle being offset from the center of charge. And every time people measure it, they get something consistent with 0, but the error bars have gotten smaller and smaller. And this slide I see is out of date. The current limit is down around 10 to the minus 29. It's improved 2 orders of magnitude. And which is a very, very small distance. To put it in context, it's hard to describe the radius of electron, but you can come up with various ways of defining the radius of electron. And this is, if there's an offset between the center of mass and the center of charge, it's about 15 orders of magnitude smaller than the radius of the electron. The electron is very, very symmetric. And yet these tireless theorists keep telling us, no, you experimenters are just lazy. Go look harder. We say, it's not so easy. So we know, don't do it anyway. Okay, so we do it. So that's the JILA electron collaboration. Here are the current group of students and postdocs working on the project. For many, many years, this project has been jointly co-advised by Jun Yi, one of the great precision metrologists of our time, which has been hugely influential in this project, enabling, I would say, plus all of the current graduate students and postdocs. It was enormous relief for us to bust out not so long ago onto outside, and it was great to see each other's faces again. We have worked, continue to work with John Bone and Bob Field and theorists in St. Petersburg. But a couple of things I want to mention. One is just on my mind, Tanya Rusi just yesterday became Dr. Tanya Rusi. Yay! She gave a very nice thesis defense, and we're very proud of many distinguished alumni who've worked at this project over the years. And it's been a long time. This project is extended for just about 1/3. Sorry, I got that wrong. It turns out to be about 1/4 of JILA's 60 years. Which is quite astonishing. It's been around for a long time, and we're gradually getting better and better at it. June and I are the nominal PIs, but we worked extensively with John Bone and Chris Green, JILA fellows, and wrote papers with them, especially in the early years when we're thinking about how the experiment should work. Not documented in co-authors are my discussions with the physical chemists here. David Nesbitt, Carl Lineberger would let me come into their office and say, okay, what's a molecule again? How do these things work? How do you detect them? Vibrations, rotations, omega doubling, and they had answers for all these things and made it possible for me to do these experiments, even though the last chemistry class I took, I was a sophomore in high school, and so molecules for me have always been kind of scary. We have benefited from thousands of hours of design and construction from the JILA shops. To make this happen, we had to submit and then have administered many, many grants. We purchased enough stuff to fill up many large rooms. We've taken dozens and dozens of trips, which require these days a lot of coordination. We've tracked mud up and down the corridors, and someone kept them clean. One way or another, almost over the 18 years, there's very few JILA staff people that haven't been involved in helping us make this experiment work. And people have mentioned this before, but thank you, JILA staff people. Just amazing. Okay, so how do we measure something? This is a tremendously precise measurement. How do we make things this precise? There is the first law of experimental physics, which is if you want to measure something very carefully, figure out how to take the thing you want to measure and turn it into a frequency, and then measure the frequency. Because if there's one thing that physicists are good at, especially JILA physicists, is measuring time. Which is, by the way, 1/frequency. That's a result. 1/frequency, that's time, vice versa. So I might say time, I might say frequency. I think of them as the same thing. Indeed, there is the time and frequency division. When you think about it, there's something. Okay, anyway, all right. Here's a clock. It actually was for its day a very good clock. And what makes it a good clock? Well, it's got a pendulum, and the pendulum swings back and forth. Why does it swing back and forth? Because gravity. When it's swung out this way, gravity pulls it down. When it's there, gravity pulls it the other way because you can see gravity is kind of at a little bit of an angle. So gravity pulling down there causes it to swing back. And if you ask how fast does it swing back and forth, it swings back and forth. It swings faster. As gravity gets stronger, it swings faster. If gravity gets weaker, it swings slower, I should say, at a slower frequency. Here at JILA, we can measure small changes in the frequency of your clock out to 18 digits, which means in principle, we could measure the frequency of a grandfather clock. And if the grandfather clock changed its frequency by 1 part in 10 to the 18, we would measure a change in gravity at that level. Now, it turns out that we're actually able to say things about gravity, not exactly in this way, but this is an example of taking a physical property, gravity. How do I measure gravity? Well, I could sort of see how heavy things are. I get this, that my laser pointer is pulling down on my hand, and I could say, yeah, that feels like there's some gravity, all right. Oh, maybe it's not quite as heavy as it used to be. Maybe it's a little lighter than it used to be. Gravity must be changing. That's a very hard way to measure it. But if I could somehow turn that into a frequency, I'm not saying I could measure gravity to a part in 10 to the 18, but you can do pretty well using this kind of thing. So frequency, we need frequencies, but we're not measuring gravity. Here's another example. How strong is a magnet? If you took a compass, you know that a compass points towards the North Pole. The South Pole of your compass points to the North Pole of the Earth. If you wanted to know like how strong this big South and North compass magnet is, how strong the magnetic fields are, you could put a compass needle in there, and the North Pole gets attracted to the South Pole and it'll oscillate back and forth. And if you measure how fast you pull the needle off and it'll go twing, wobble back and forth. And if you measure how fast it wobbles back and forth, you'll measure how strong that magnetic field is. If it happens to be, and that's basically how MRI works. Sorry. If it happens to be that instead you're interested in the electric dipole, you could take your magnet and you could spray a little positive stuff here and a little negative down here. And if you do that, you may find that the frequency that the electron wiggles back and forth at changes a little bit. And if it does, that's the electric dipole moment. That's all we do. We basically take an electron and we put it in a magnetic field and we add a little electric field and we see if that wobble frequency changes. And we compare that wobble frequency to JILA's immense capability to measure frequencies to 18 gazillion digits. Maybe not gazillion digits, but over a part per gazillion anyway. Maybe even a part per bazillion. I'm not sure. It's a lot. But there are two. But if we want to measure, if this is a small dipole moment, we need to apply a really large electric field. One big problem with that is you try and make a big electric field in the lab, you get lightning sparks. They just jump from one metal plate to another. And the other thing is that electrons themselves are charged. And if you apply, check this out. That is high-end skills with PowerPoint. Yeah, the electron gets pulled over there and you can't look at it for very long. Where can we find a really strong electric field? Well, when I was a sophomore in high school, I learned something very important, which is how molecules stick together. They stick together because one atom is positive and another is negative. Isn't that right, David? That's how, actually, people say, no, that's not how most of them really do stick together. Humor me, because as I said, this was my level. And so we learned that there's sodium chloride, and we learned that the sodium is positive and the chlorine is negative. And just imagine if you could somehow live inside that little space inside the sodium bond, there'd be a really big electric field there. Unfortunately, sodium chloride has an even number of electrons and there's no leftover electron spin. So we work with hafnium fluoride plus. Hafnium is very, very heavy. Fluorine, and I did learn this in high school, is very negative. So in fact, hafnium is positive, fluorine is negative. One is very heavy, which turns out to help for reasons I won't describe. So what else do we need to compare things? I said we want to measure times, compare times very, very closely. And so suppose we have two grandfather clocks and we want to know which one is ticking faster. So what you do is you might wait for a minute and count one clock, and one clock counts 60 times, and so does the other count 60 times. Well, I guess those two clocks have exactly the same frequency. Is it exactly the same frequency? What if we waited for an hour and one of them ticked 3,600 times and the other ticked 3,600 times? Well, now we can say not only are they exactly the same, but they're exactly the same to even more accuracy. If we waited for a day, maybe we'd notice that one of them ticked one time faster than the other. And we'd say, yeah, number two, that's a slightly faster grandfather clock. If you want to compare frequencies really well, you got to be able to count the ticks for a long time. How do we count the ticks for a long time? Well, we need to put our hafnium fluoride plus thing in an ion trap. And here's a classic example. Oh, not of an ion trap. That's a rabbit trap. there's an ion trap. Basically, we use rods of metal and we charge them up, and there's a artist's conception of an ion floating there in the middle. And these are big. These are like 4 or 5 inches across, maybe 10 inches long. And right in the middle there, the ions sit in a little glowing ball about 1 centimeter across. Did I just go from inches into centimeters? Am I in the presence of a high-ranking NIST official? This is all very worrisome, but okay, hopefully this is not being taped. Okay, so this actually is 1 generation ago, but I still show this picture because it's a particularly pretty trap covered with gold. You may be able to see 6 rods coming up here, and it's set off very nicely by this sort of azul background. It turns out that covering gold is a bad thing to do to your ion trap, but who knew? And then we watched it. This is basically watching the thing tick. It ticks relatively slowly here over the course of about a second. This is about a second here. It's ticked about 10 times. We do the, how do we listen to the clock tick? We use lasers. We have an entire room full of lasers. When I was a postdoc, I did an experiment with 2 tunable lasers. I thought I was pretty badass. 2 tunable lasers. This experiment is done with 14 lasers. And it's, you know, it's not that it's that many times harder. It's just that lasers have gotten easier, commercial. And here at JILA, we're really good at lasers, you know, so things have gotten, but it does mean that you have an entire room full of lasers tending to one little place where the grandfather clock is ticking, which is way back there. I'm almost out of time, so I'll tell you that we make these molecules are unstable, so we make them in situ and trap them there inside the trap, and then we watch them tick. We use many lasers, and it's a very complicated sequence. Fortunately, there's a computer which keeps track of all those things, because even very talented graduate students might forget to apply the 57th pulse that's required. So it's all done in a very automated way. We count these ticks. We count the ticks 2 different ways. Once with the molecule stretched up so that the electric field's coming down, and once the other way, so the electric field stretched up. We keep going back and forth, should tip the molecule over, tip the molecule over. We go back and forth, and we look for very small changes in the clock frequency. And that's basically the experiment. This is actually, we want to make sure that we're measuring what we care about and not some odd signal. So we move the ions around the trap, and we characterize how the frequencies depend on the location, and we learn very interesting and troubling things about inhomogeneous fields, and we solve them. This is from our measurement in 2017. One of the things that made it tricky and still makes it tricky, or at least stressful, is that it's so easy to fool yourself. You know, if you really want to see a non-zero electric dipole moment, what you're going to do is you're going to say, oh, today we measured the average today and it seems non-zero, but yesterday's data was 0. There's probably something wrong with yesterday's data. Let's throw that out. You do that enough times and you'll get yourself a non-zero average, and it's really hard not to do that. I'd like to argue that I am no more dishonest than any other physicist and more honest than some of them. All the same, I would have a lot of difficulty resisting this temptation. Why subject yourself to temptation? Put a lock on the refrigerator door, whatever it is. And in our case, what we do is we tell the computer, lie to us. Take every time we take half an hour worth of data, add a number onto it. Don't tell us what that number is. And so all of our data come out. You can see that's like a year's worth of data. And it always seems a little different from 0. We didn't get excited about that difference from 0 because we knew that's what's called the blind. And then there's this very dramatic moment when you remove the blind, and bang, you see what it is. That was a very stressful moment. That was about 4 or 5 years ago. And we were in very tight competition with Harvard and Yale. We measured, they measured. We both got numbers consistent with 0. We were co-collaborators, you might say, on a terrible crime. And that crime was the murder of the minimal supersymmetric model. Actually, Large Hadron Collider had a lot to do with that as well. So there was the Large Hadron Collider, there was these 2 dipole moment experiments, other dipole moment experiments. All of these things went to make, basically, no one really believes in these simple versions of supersymmetry anymore because of these inconvenient experimental data. Supersymmetry was so good before there were any measurements. Now it seems less fashionable. And we helped kill it. So we feel weirdly satisfied about that. We would have preferred to actually see it, but you do what you can do. But then something terrible happened. Harvard and Yale went and measured another number, also consistent with 0, a factor of 10 better. I know this television show is now rather old, but I love this line. That's just rude, says Villanelle. And so, yeah, we have bounced back. I realize I have like a minute to go. I'm thinking, yes, more or less. Are you like a minute? We bounced back. We have the last 5 or 6 years, we've made the experiment 10 times better. We are within a few weeks of announcing this experiment, which is 10 times, actually, no, 20 times better. Not only 20 times better, it's a factor of 2 better than the ACME group. And I would actually prefer, when I mentioned the ACME group, if everyone would go like this. Just kidding. I know all 3 of them, the 3 of the professors, they're great, except that they're also our rivals. What are you going to do? So individually great, collectively the evil empire. And so we will soon have a number, but what will that number be? What we can tell you is, I don't know, it's still blinded. This was the ACME measurement, 4 plus or minus 4. By tradition, people will report that as a limit. They'll make it symmetric. They say, we think it's less than about 10 to the minus, basically, plus they say, we have a pretty good confidence that it's less than plus or minus 10 in these same units where they get 4 plus or minus 4. So you expand your error bars, make them symmetric. We are going to be, our error bars are going to be a factor of 2 smaller. If we want to turn that into a limit, it depends on what the number is. If it happens to be that we measure very close to 0 plus or minus, we'll be able to put quite a bit tighter error bars. That would be exciting. That would be good. Or what if we measure this number? This number is technically pretty much in agreement with the ACME number, which is good because we have a lot of respect for the ACME number, ACME group. We really would not have to embarrass them by showing that their measurement was wrong. So yeah, we'd like to be in agreement with them, but we could be in agreement with them and also very strongly in disagreement with 0. I don't know, we're going to measure it pretty soon. Or we could be in disagreement with 0 and erratically in disagreement with ACME, which would be embarrassing. They'd have to go back and figure out where they did something wrong, because we haven't. All right, that's about all I have to say, except that we'll have a result there soon. We're working on an experiment which is 10 times better, which involves what we call it the bucket brigade, many ion traps all working in parallel. This is the bucket brigade here. If you see each one of those, every 4 of those fins defines, actually every 8 of these fins defines a trap. This is a prototype with 10 traps. The later one will have actually 25 at least traps. This set of electrodes is many electrodes. It's a little bit like the QCCD things that people talk about, except that you can see our scale here is much larger. We brought in all these professional models to set a scale for the, actually, no, they're actually a distinguished group of scientists. And here the same group of scientists are putting in the electrodes into a vacuum chamber, sealing up the vacuum chamber and pumping it down. And first light. Oh, no, that's not our first light. There's our first light. First ions in the 3rd generation. So even though we haven't quite finished the 2nd generation measurement, the 3rd generation measurement is well on its way to making, well, it's got a little ways to go, honestly, but soon we'll have in a few years, we'll have a 3rd generation measurement. I thank you very much for your attention.
Maybe a quick question for Eric, just in case there is one before Cindy, who should be in here somewhere, I'm hoping. I see a question.
Oh, is there an, oh yes, indeed. One of the wonderful things about almost any, one of the wonderful, is there an, sorry, the question is, the minimal supersymmetric model is dead. Is there a non-minimal supersymmetric model? And the answer is yes. One of the wonderful things about supersymmetry is it can predict pretty much anything you want. And so but as you add each factor of 10 to your precision, you remove wiggle room, let's put it that way. And so that measurement by ACME removes some wiggle room. Our measurement, which will unblind probably just a few weeks, will remove about another factor of 2 of wiggle room, unless maybe we see something that would be cool. Yeah.
All right, with that, I think in order that we start the prize session on time, let's go ahead and have Cindy come down. And all right. Our next speaker is Cindy Regal. Professor Regal is a summa cum laude graduate of Lawrence University. In 2001, a PhD in physics right here at the University of Colorado, 2006. She went on to do a prize postdoctoral fellowship at Caltech. And before returning, kind of a theme of these speakers to JILA and CU, where she's currently a fellow of JILA and the Bauer Associate Professor of Physics. She has won numerous awards, including the Cottrell Scholars Frontier in Research and Excellence and Discovery Award. That was, I guess, just 2 years ago. The CoLab's Colorado Governor's Award for High Impact Research. The Provost Faculty Achievement Award. She won both a Presidential Early Career Award as well as a Packard. And Cindy, I gather the title of your talk is Mechanical Quantum Systems, Harnessing Radiation Pressure in the Solid State. Go ahead, Cindy.
All right, well, great. Thank you, Konrad, and thanks for the opportunity to be here and see so many faces that I've seen over time in so many different ways. And I think I'm gonna stick on the title slide for one more moment. Yeah, so thank you, Carl, for your presentation. I always enjoy hearing about JILA history, right? There's things that I've heard and some stories I've heard many times and some stories that I haven't heard yet. And so I learned a few new ones. You know, I think you're now going to hear a talk from someone who's, I guess, has never seen a typewriter in JILA. I think, although I think I've been around long enough that I've seen, I've used a few floppy drives for sure. And, you know, given the electronic shop maybe he still has a few instruments that use them, I might even be still using them. All right. And also, you know, what I would like to talk about today is a story that I think helps indicate how much younger fellows learn from all the things that have happened at JILA over the years. So I'm going to tell you about mechanical quantum systems that we make these days out of solid state objects, but really harnessing something that's been used in JILA for a long time, radiation pressure and laser light and how they can push on these objects. So to make this point, I sort of pulled a picture out of the archives of JILA, which is showing some atoms that are inside this vacuum chamber here being cooled by pushing on them with laser light. And this is sort of one of the stages of cooling of atoms that led to Bose-Einstein condensates, the Fermi gases that Debian created. And in these type of experiments, what you're really doing is you have this ball of atoms and it's isolated from its environment because there's a vacuum between where these atoms are and the walls of this chamber here. And this is being applied in JILA to molecules and many other things. But what I'd like to tell you about today is what if we think about this sort of radiation forces that we can apply to these atoms, but we think about really, you know, a real solid state object like this. And we can ask some excitation of that object, which you could think of as if I took one of those excitations, it might be a mass on a spring. And if you know acoustics and sort of solid objects like this, it's often hard to isolate, you know, sort of a single mass on a spring. But I'll show you some devices in which we managed to do this. And we managed to use radiation pressure from light sort of cooped up in a bottle between two mirrors to push on this mass on a spring. And this mass on a spring, to us, thinking about quantum systems, for those of you who are familiar with these ideas, this is a harmonic oscillator for the most part. And so I'll show this picture here where I have different levels in this harmonic oscillator quite often. And in the context of this analogy to laser cooling of atoms, you can sort of mock up these systems to use light that is red detuned of something that you often do in laser cooling. In this case, it's a cavity resonance. And you can actually push on these objects in such a way that you apply the right forces at the right time to actually damp and cool their motion. And this is sort of a toolbox that we've been working with over the last decade here between the 50th and 60th anniversary. And I'd like to tell you some of what we've done and some of what we're trying to do. So I'm going to show you a few pictures of some devices with which we do this these days. And these are made in all variety of the JILA shops. So there's different components that are made, metallic components, fabrication components, and they all come into making these little widgets here. So the first one at the top here is one of our masses on a spring. And it's this black thing here is a silicon chip. And stretched across that little hole that you see in the middle there is a very thin film of silicon nitride. And if I were to sort of pass this chip around and you sort of turned it around like this, you would see it glinting at you. So you could see this really thin film. And so it's about 0.5 millimeter on a side, but it's very thin. So it's about 50 nanometers thick. So that also makes it fairly light. And it'll vibrate in a pattern that's sort of something like this is often the vibrational pattern that we use. In JILA, there's also drums that are made of metal that you can detect with a circuit instead of laser light. And this is a false color image where this little yellow pad here is sitting very close to something else on this chip, and it moves up and down like this. So that's our mass on a spring that we're isolating in that case. And then there's much more complex circuits that are being made at JILA that isolate, for example, surface acoustic waves between different electronic components. There's many different false color bits all over here, but this is illustrating that we've now come into a regime where really that mass on a spring, what we call a phononic degree of freedom instead of photonic, the N in there, we can actually count how many phonons are in there, which we think of as a pretty quantum thing. So we can tell in this little plot here whether it's 0, 1, or 2 phonon excitations of a little surface acoustic wave that's trapped in between there. So these are some of the questions that we're asking now that we have this ability to really control these type of excitations in the solid state. One of those questions is this type of motion that we control it really well. Can it connect quantum, microwave, and optical signals? Can we actually manipulate or say squeeze light using motion and use it to better measure in interferometers? Can these acoustic waves be compact interconnects between superconducting quantum bits and help us make quantum computers? What are the most isolated we could make our mechanical objects? So these questions are not just being asked by my group, but a variety of folks in JILA, one notably Konrad here, who is not only a leader in this field, but really one of the inventors of thinking about these mechanical objects and how we push on them with radiation pressure. And so some of these questions are being asked by his group, some by my group, and then some of them, like this one here, we're collaborating. So Konrad pushes on his mechanical things using electrical circuits, and I push on them using laser light. And we found ways that we can sort of combine these to solve hard problems. So I'll tell you about some of this. Being in JILA as well, you run into many people in the hallway and many JILA fellows in particular. So there are a number of theory groups in JILA as well, who we've talked to over the years and worked with to try to answer these questions. So the questions that we're talking about here are often have to do with what I might call solving some problem in quantum technology. So we want to control quantum bits. We want to make different systems where many different quantum degrees of freedom interact. Are there ways that mechanical excitations actually help us? And that seems a little bit odd, right? That you usually think about photons or electrons. So an actual mechanical solid state degree of freedom seems like a little bit of an odd choice. So when thinking about different types of technologies and what works better in different contexts, there's different stories that I think about over time. And being here at JILA, even though I don't make clocks, I can't help reading about clocks or thinking about them or making analogies to them like Eric did there. But I don't know if anyone's ever read this book here. It's a good one if you haven't. And it's actually about a story of sort of navigation and the longitude problem, and thinking about what technology was right in that particular moment to solve that problem. And it really came down to sort of using the heavens to guide us or making a widget, right? A mechanical widget. And the book is set up in such a way that you're rooting for the mechanical widget, all the way through the book. And for that time, indeed, the mechanical widgets helped solve this problem. Of course, you know, things ebb and flow in time, right? And now when June makes his clock, he's relying upon nature and the pure thing again, right? But there's different things that sort of help us solve different problems, and sometimes they're surprising. And that's sort of where I put these mechanical systems and sort of what kind of surprising problems can they help us solve. Okay, so with that, I'm gonna move along to these different questions here. And I'm not going to talk about this one so much here. You can chat with Konrad at some point if you want to hear more about that. But I'll talk about these different problems and try to introduce you to some of the concepts and measurements that we make in our lab. So to introduce this idea, what I will try to do is just ease in by not talking about it from a sort of measurement perspective. All right, so we're trying to measure this mass on a spring. We're trying to just tell, you know, how much it is moving. And as we heard, an interferometer is a good way to do this. And people have made interferometers at JILA for some time and ask how well can we make them. A Michelson interferometer is a nice one I like to start with, because if you've taken a freshman physics class, it's often the type of thing that you work with your lab partner, and you try to see some fringes of your Michelson interferometer. And it's one of those cases where maybe if your lab partner is bonking on the table, it's a little hard to tell what's going on. If you get them to quiet down and not bonk on the table, there might be seismic fluctuations, right, that can cause the mechanical excitations within your interferometer. If you get that to calm down, there might be thermal excitations of those mirrors. And if you get that to calm down, then you could ask sort of fundamental questions about how well could you measure the position of this mirror using light in this interferometer. And what you do, right, is you take a laser beam and you split it into two paths, and you can determine this differential path length difference by measuring the output photocurrent on this photodetector as a function of that. And if you sit on this edge right here, you can tell very well how much has that displacement changed. And this Michelson interferometer, like I said, is a common measurement tool in your freshman lab, but also for heroic tasks. So this is like how the LIGO interferometers work, right? Trying to tell the differential positions between objects like this. So if I think about how well can I sit on the side of this fringe here and measure, well, eventually, when I get rid of all those problems that I was talking about before, I would be limited in signal to noise by what we call shot noise, Poisson distributed photons of the optical field that I'm using to measure this object. And so thinking about this problem has some history in the context of measurement science. And let me just think about it a little bit from what one might call a sort of Heisenberg microscope argument of how we think about measuring how well can we measure the displacement of this object. And if I'm thinking in certain ways, or I'm just going to do back of the envelope calculation, I'm thinking in a time small compared to an oscillation period, and I want to measure continuously, so I'm going to measure more than once. If I measure this to some delta x at some time t, and I measure better and better by putting more and more light into this interferometer, I will actually end up with a momentum perturbation that's given by this constant h bar that comes into sort of all quantum problems. And if I think about this in terms of, well, I've measured so well in x, and I have some perturbation in momentum, at some later time, I have how well I measured in x, and I have something inversely proportional to that x. And that in the end means that I only can really measure so well using this light in this back of the envelope way. And so this is a long-standing problem in thinking about interferometers, and then one that we can actually explore by looking at the motion of these type of objects. So we did experiments where we have vibrating motion in one of these really little thin films, and we have photons that are impinging on them. And in this limit of Well, I can actually see the photon recoil on this mechanical object. I'm really seeing this perturbation of the momentum of that object. But seeing that for a really big object is hard. And so even though these types of thought experiments had been considered for a long time, really seeing this for a solid object was hard, even though for atoms, we see recoil all the time around JILA. So to do this in the laboratory, we use a number of different things. We use low noise lasers, so laser tables that look very familiar to those who have walked around JILA. But we also do some new things. We take these type of devices to cold temperatures, so 100 millikelvin scale, and they're really connected to their environment, and that environment ends up being cold. But we can shine laser light into such a cold environment these days. And if we do this, we can actually not only sort of measure these objects at this limit that I was talking about before, but we can also manipulate that light. And one way you can manipulate the noise of light is you can squeeze its distribution in this way here. And so I could measure better along this axis than this axis. And this is an old idea of manipulating light using motion that's actually called ponderomotive squeezing. And so I have sort of radiation pressure noise associated with that shot noise and light amplitude. And the mechanical system can actually write back onto the cavity in the phase in such a way that my noise actually gets modified quite a bit. And I have noise that's below the shot noise. In the end, this type of measurement where I can get noise below the shot noise can be helpful for measurement. And it's also a very sensitive measure of the efficiency of the system. It's a nuance, but it tells me a lot about whether I'm losing photons in the system. And this is really an example of sort of manipulating quantum light using the motion of an object, which is a theme that we'll come back to a little bit later. Okay, so I think from that perspective, I'm just going to give you a little snapshot of type of things we were able to study by the fact that we could manipulate this light with motion, in particular create this squeezed light. So if you have some limit that I was describing before, how well could I measure this position of an object with an interferometer? Well, I'm actually able to measure better in certain parts of frequency space by utilizing this motion to manipulate the light. And I think somewhere in the cyberspace between PC and Mac, I think some shading was lost in this plot here. But nonetheless, this is sort of a model system where we're learning about quantum sensing and interferometry and how motion and radiation pressure can sort of interplay in an interesting way. So with that, I'm going to go on to what seems like a very different problem, but hopefully with this sort of measurement aspect in the backdrop of how I think about this problem. So a lot of what I'm talking about is really, as I said, sort of quantum technology. How do we take quantum states and utilize them for interesting things? So this is an image where someone has decided, well, I'm going to have some quantum system that I'm going to label as an atom here in one continent, and I'm going to send some information to another continent. And the only way I can really imagine doing that in a robust way is if that information in this sort of train of zeros and ones is up to actually at optical frequencies, at energy scales that are really robust to a room temperature environment. And these nodes here, if Konrad has his way in the context of experiments, he would have those nodes be superconducting quantum bits. In the electrical domain, it's actually very easy these days to manipulate quantum information in that way because you have sort of very strong ways that you can control the state space of the system. And the problem, though, is if I have these nodes here be in the superconducting domain, I can't really get the states out to be sent elsewhere. And so this is sort of one of those problems that people are trying to solve. And we illustrate it in this way, which is that it's wonderful to have interesting quantum states. Sometimes they can be cat states, right? Superposition of dead and alive. But often they're sort of stuck in a low temperature environment. So are there ways that we could actually get those states out into an optical state where they could end up making these links? And you might think that that should be a relatively solved problem these days, right? An electrical signal to an optical signal. But in the context of quantum problems, this is really quite unsolved. And it's one of those things that we're now pursuing, both to do this long distance networking, but also ways that you could interconnect qubits down in the bottom of a dilution refrigerator at these very cold temperatures. So this is what our devices look like these days, where this green thing here now is a stand-in for these vibrating solid state degrees of freedom, which, as I've told you, we can cool, we can measure really well. We've learned how to do this over time. And via various different aspects of what we do at JILA, we can both measure them optically and measure them via an electrical circuit. And in fact, we can do them both at the same time, in the same building, in the same lab, in a lab where Konrad and I actually operate jointly both optical and electrical systems. So in this system, let me explain a little bit more about how some of the couplings work. So this guy over here, right, I showed you this picture before where we're sort of pushing on an object with light. It turns out that if I put that object in the middle of a cavity like this, I can also effectively push on it with light. In the electrical domain, what I'm doing here is I'm actually changing a capacitance by changing a distance between two things. And by changing that capacitance, I change the resonance of this LC circuit that we have here. And I have exactly the same interaction in the two domains. And I put a big sort of star there because you might think if I hadn't sort of led up to this and talked about why megahertz mechanical excitations were something you might want to use or could imagine using in a quantum context, you might imagine that it's a pretty silly thing to do to take some high frequency excitation in either of these domains, convert it to something low frequency, and then send it back over. But as I'll show you, this turns out to be a good plan in the context of making it a very efficient link between these two domains. So if you're familiar with sort of optical tables, and if you look at optical tables at JILA and you say, I have a classical sort of signal that I want to think about sort of modulating in a certain way to connect electrical and optical signals, it's very common that you can just buy a widget that looks like this. It's called an electro-optic modulator. It has a crystal in it called lithium niobate. And it's very common it could potentially achieve these type of metrics that we were talking about of really converting microwave to optical signals. So why not use such a device? You know, my answer in general is these devices where we're really controlling mechanical motion, we're sort of engineering nonlinear materials. So instead of pulling a crystal out of a drawer, we're utilizing radiation pressure, have flexibility in materials and geometry and size, and can make the interaction that we want. Okay, so what do some of these type of objects look like? So as I said before, we have these very thin films that are stretched across this frame, and they vibrate at certain frequencies and in certain patterns. And this dielectric film is very easy for us to sort of push on with light. But in order to make this capacitor spacing that we have to do to couple to an electrical circuit, we have to have a superconducting thin film that sits on that object. And that superconducting thin film we put down over at NIST in the NIST clean room, and it allows us to couple to the electrical circuit. We take multiple chips and we put them together such that distances between different objects are very, very small, scale of hundreds of nanometers. And we do this without trying to get the whole thing to be 100 nanometers, but not zero, right? So we don't want it to collapse upon the other part. And then we put this object inside of an optical cavity where we're utilizing resources around Boulder. For example, these mirror surfaces here are super polished mirrors that are made in a very specialized company that's just out in East Boulder. Okay, so this is what one of these devices looks like. And it looks like quite the monstrosity in some ways. So there's a mirror here, there's some epoxy here. It's a very special epoxy. It's an epoxy that doesn't crackle when it gets very cold. And then we have a device inside of here as well. And then we have an optical port, which is simply a hole with which light goes through. And we have a microwave port, which is an SMA cable that goes in. And we can measure this device in a variety of ways. And one of the things we can learn is about the efficiency with which we would be able to convert a quantum state between a microwave signal and an optical signal. And in these devices right now is about 50% efficient, which is the best of any device that people have made. And it's not quite quantum. There's a few factors that we need in order to get there. But it's something that we're pushing on in terms of some of the materials of the device. But one of the big questions that we've been asking ourselves for this whole time that Konrad and I have been working on these type of devices is it's really a very large energy difference between the laser light that I use and electrical circuits that are required to make these quantum systems that are very cold in the superconducting domain. You have one optical photon that hits a superconducting thin film, you create quasi-particles, you create noise. And so, Konrad is our fearless leader at JILA, but he's afraid. He's very afraid of my photons. And so for a very long time, we thought, well, the type of things that we would need to do to put this together, we would worry that we would sort of mess up the superconducting circuit and we would create noise and that would be a problem. And in the context of just the transduction, it's turned out to be pretty good and we're pretty happy about that. But we've recently been asking another question, which is that now I actually have a superconducting quantum bit in the system, right? This thing where I have the 0 or 1, it's very sensitive to anything even beyond this sort of LC circuit. So we recently now have experiments where we have in our refrigerator system here that's very cold, we have our transducer that has this LC circuit and this optical cavity. And we have our what we call our qubit cavity over here. And these are both sort of very close to each other now, sort of dangerously close. And we've been asking questions about whether can this qubit survive when we put light into the system and try to extract that state into an optical photon. And this looks like a pretty complicated diagram here, so I don't want to scare you, but I wanted to show different components that go into this. So we have sort of a cavity over here and a qubit, a bunch of electrical components. We need to pump the system with microwave and optical light, and then we have our way that will eventually get our signal out here. And we were afraid. We were afraid these are too close. We were afraid optical photons would really be causing a problem. But it turns out that our optical cavities, I think really because of some of the precision techniques that we use at JILA, they scatter very little, right? So we're able to really confine the light where we want it to be confined and not get into the system where we don't want the photon to hit. And the lots of light is really sort of really confined in this optical model here. So we were able to do some measurements. We're actually able to read out the state of this qubit onto an optical signal, not quite in a quantum domain because we still have a little bit of noise there, but in such a way that by doing some tricky measurements, we could show that the qubit really preserved its information even when we had all of that optical light there. So this is something that we're quite excited about, and Konrad is not as afraid of me as he was before, I think. All right. Okay. And next step is really trying to move towards quantum states and really ask whether we can have this be an efficient conversion process and no noise. So I wanted to spend the last bit of time here sort of focused on the idea of, I told you at the beginning that we were going to take this mass on a spring, we're going to isolate it from all the other sort of acoustic excitations that there are. And we think about this in terms of what I think about as a quality factor. If I put energy into some excitation, how long does it take that energy to leave, right? And conversely, I can think of that then as how long does it take for some bad things from the environment to leak into the mechanical excitation that I care about. And as I said, there's, if I just think about some solid chunk of material like this, and I have some acoustic system where everything is coupled, it's hard to get a really high Q oscillator out of that. So we have to do some pretty specialized things in order to really get the mode spectrum to be what we want it to be. So in the context of these transducer experiments that I was discussing, what we have is some little periodic array of masses that help us isolate this mechanical mode from its environment. Taken to a sort of limit where we were studying these devices, what this is a periodic array of silicon masses that's surrounding this little drum that's supposed to be vibrating at a certain frequency. And that periodic array of masses actually makes a band gap in the acoustic spectrum and helps us keep the energy in this mode for longer. And this has been quite influential in our ability to really control that particular mechanical excitation, make sure it retains the information that we want and doesn't lose it to the environment. So we've been pushing along these lines of asking, how well could we make this type of acoustic isolation? How well could we sort of keep all the energy in the mechanical excitation for as long as possible, right? So that it's a little even closer and closer to this regime where the atom sits in the middle of a vacuum chamber and doesn't touch anything else, right? In that spirit, we've been studying some different structures over time where we take these micromechanical systems, this idea of this acoustic bandgap spectrum that I would describe as a phononic crystal. Tension suspensions, really sort of pulling these films across the structure, and also really quite intricate designs, which gives us a huge complex space to work in. We can think about the limits of the sensitivity of these type of devices and think about what ways we could detect different types of things. For example, spin systems, even perhaps nuclear spins. And in that context, you can imagine measuring displacement, forces, accelerations, and making really quite intricate structures with little defects that vibrate like this, for example. So what this structure is it's a periodic array of masses via silicon nitride, which is this little light blue stuff, and sort of a hole in the material, nothing there where the dark object is. So you get this really nice periodic array of masses, and you really need to figure out how do you put this defect in the middle in a way where it does what you want it to do. But this is a vibrating mode of what we call the snowflake because it looks pretty and a bit like a snowflake. So in this way, you can really part the waters of the different modes of the system really quite exquisitely. So you could make this band gap in the acoustic spectrum where if you look out in this phononic crystal domain, you sort of really see nothing there. So isolating these mechanical modes better and better, I think will happen, and it will happen through our ability to really design these type of cool structures. So with that, hopefully I've told you mechanical systems are interesting. We push on them with laser light, like all of our forefathers in JILA have told us how to do. And we really feel like we're now pushing this all into the solid state, connecting to superconducting qubits, and connecting with many great students and postdocs. So it's been mentioned that the staff, the people here at JILA make everything work. And of course, the students and postdocs, I sort of put a smorgasbord of them here to indicate how much excitement we have here at JILA based upon all of these young faces. So thanks for your attention, and I'd be happy to answer questions. Okay. Yes, David.
Cindy, you mentioned something sort of interesting about that you had this, that your glue, your epoxy was special in that it didn't crack when you went down to these 100 millikelvin temperatures. So what's special about the epoxy? Does it match the thermal expansion? Because it's really hard to make things sticky when they're cold, right?
Yes.
It's sort of an
exactly.
unsolved problem in general. Yeah.
Yep. You get to keep the microphone. Okay. All right. Great. As David asked the question, he's my most frequent question asker at all of our PSC meetings, and we had wonderful discussions about optical tweezers the other week. So this is a question that I did not solve. This was probably solved in Cornell maybe far before that.
Well,
so,
the National Starch Corporation.
Yeah.
in the
Okay.
1970s,
Yeah.
but,
Okay. Yeah. Exactly.
Figured out in the 1980s by the guys in the H-wing corridor.
Yeah,
Cornell.
exactly. Yeah. So the particular epoxy is die-cast. It's very black, and it's specifically designed not to get brittle cold, and that's pretty important. Yeah. Yep. So we did our low temperature physics homework, and yep, chose the right thing.
Thank you.
I'll just make a comment, which is I don't think it was so much you that were scary, but the lasers that you brought. That was. Other questions for Cindy? I see one over here.
Yes. Oh,
Sorry.
Hi. You mentioned converting microwaves to optical waves and back in, I think, the quantum realm or in some quantum perspective. Could you elaborate on what you meant by that?
Yes, that's a very good question in the sense that I say quantum this and I say quantum that, and in this length of talk, there's not much that really backs that up. But in the context of quantum systems, there's many degrees of quantumness. One way I could answer that question is I could say I want a single photon, and I don't want to think about it as a wave. I want a photon. And I have some stream of photons that has a non-classical nature, and I could see that stream of photons on the other side. That might be one way to think about it. I could also imagine that what I want to do is I want to show some non-classical correlation, some entanglement between some signal that I have on one end and some signal that I have on the other. And really sort of maintaining entanglement between long distance over different nodes is one of the things that's really required in the context of utilizing quantum as a resource.
Thank you.
Did I see another question before I? No. Okay. With that, I think we'll close the little symposium here. 4:45, looking at Beth, making sure that I'm getting this right. 4:45 begins the award session over in the case building. If you don't know where that is, just follow the crowd of people going over there. There'll be refreshments after the presentations over there, which will attract many of the graduate students. So, yeah. Thank you to all of the speakers, and thank you for you to come here. Thank you so much.